Welcome to CSE 31 Lecture 14. Hope everyone is doing okay right now. And from now on, we're going to use video clips as lectures so that you can just review this video on your own time. Okay. And also, I would like to divide each lectures into smaller video clips so that you don't have to watch the whole hour because it's sometimes pretty heavy. Okay, so just pace yourself and you read the lecture and then watch the videos as you can. Okay. So before we start the lecture, here is our announcement. Okay, so project 1 due date has been postponed to Friday, April 3rd, which is the Friday after we come back from spring break. So I don't think we're going to come back to campus after spring break, but just be informed that from now on, most likely our classes will be conducted online. Okay, so when I say Friday after the spring break means that we are still doing online, but we still have the due date. Okay? And I'll arrange the demo with the TA so that you can use a Zoom to do the demo later. Okay? And we're gonna have Lab 7 this week. So some students have already attended the Lab 7 using Zoom. Hopefully the experience is not too bad, but keep in mind that we are not going to do any demo until we come back from the spring break because I still need to do some customization with the Zoom so that students can share the work to the TA privately. Okay. And homework 4 is online already in Zybooks. So what you need to do again is go to CAD courses and click the link and it will bring you to Zybooks. And you have until Monday, which is the first day after we come back from spring break to turn in. And make sure you click the submit button, otherwise the scores won't be reported. And tomorrow, or I shouldn't say tomorrow, but on Wednesday, March 18th, depends on when you are watching this video. The reading assignment is due, so please make sure that you turn in your reading assignment by Wednesday, March the 18th. Okay, so let's start the lecture. Last week, we talked about two different formats of machine language or representation of instructions. The first one is R format. R format is used to describe mostly instructions with registers. For example, add, or, these are all R format. So you have 3 registers as operand. And once you use R format, you will need to record 3 registers, RS, RT, and RD. And opcode is always 0. And then the operation is decided based on the function code. And you can also use shift amount. So the shift left logical, shift right logicals are considered as R format. And I format is pretty much any instructions that deals with constant. That's why it's I, immediate, right? Now, with I format, you only have opcode to decide what operation it is. So if it's add I, and I, and or I, then the opcode will tell you the particular value. And it involves 2 registers. RS is the operand that you want to get the data from. RT is where you're going to store the result. And then finally, you use 16 bits to describe the immediate. So this is I format. So please review the last lecture slides to find out what they are. And if you have any question, email me or come to my office hour. All right, so at the end of last lecture, we started to talk about branching. Branches are considered as I format. So let's take a look at how we can do branching. So Since this is I format, we have this structure. We have opcode to describe whether it's BEQ or BNE. And then in branch, we have two registers, RS and RT, to perform the comparison. And what about the immediate? Okay, so immediate describes the constant. So what does it have to do with branch? So this is something that we need to think about. Okay, so opcode specifies either BEQ or BNE, and RS and RTs are just the two registers containing the values that you want to compare. And now we need to think about the register. So especially this is a branch, right? So branch means that when the two values are the same or not the same, we are going to go somewhere. So how can we feed the destination address into 16 bits? So that's the problem, because the destination address is always 32 bits, assuming that we are using 32-bit CPU. So how can we feed 32 bits into 16 bits? We just can't, right? So now we need to work things around and see how we can utilize these 16 bits to store the address. Okay, so before we go into how, let's think about when do we use branch? Remember when we talk about branch, we use branch for if-else statement and loop, right? So if this is true, you go to there, right? Otherwise, you continue to do something. Or you use a while loop or do while loop usually, right? You do something and then you do the test. If it's true, you go back and do it again. So we usually use branches for if-else and loop. And if you think about loops or if-else statements, the bodies are not that big. Usually it's like maybe 50 to 100 lines of code. So the distance where you're actually branching to is not that far. So keep that in mind. And with function calls or the unconditional branch, we only supply the address, that's all, right? So this has nothing to do with branch. So we don't have to talk about that until later. So let's just focus on branching. Right? So now we know that when we use branch, it's usually just if else or while loop. So the body itself is not that far. The branch distance is not that far. So, which means that we don't have to actually spend 32 bits to describe where you're going to go, because you know that it's very close by. So it doesn't make sense to use that many bits to store this kind of information. So it comes to an idea of relative addressing, or we call that PC relative addressing. Means that based on where you are you going to go from where you are? So this is called PC relative. So instead of supplying the exact address, we just need to supply the increment. For example, I'm going to go to 3 lines later. So then instead of recording the full address of 3 lines later, we will actually just say 3, so that you can add the 3 to your current address. And that will save you a lot of bits to encode. With that said, we have 16 bits, which means that we can go plus and minus 2 to the power of 15 bytes as the offset, right? Or the PC relative addressing. So which means that we can go from PC minus 2 to the power of 15 all the way to PC plus 2 to the power of 15 bytes away, which is pretty far. Okay. But if you think about how we store instructions, how big is an instruction again? How many bits in an instruction? Remember? Magic number, 4 bytes, right? So which means that between each instructions, they are 4 bytes apart. And that gives us that the address of each instruction will end with 2 zeros, which means that we don't have to actually use the offset as byte as unit. Instead, we can use words as unit. which means instead of going plus and minus number of bytes from your PC, you can just say plus and minus the number of words in your PC from your PC, which give you 2 extra bits, right? Because you save the 2 zeros. Now, you can actually do 2 to the power of 17 bytes now, because you assume that the last 2 bits are 0. So now you have 4 times as much, or you can say 4 times more than what we originally have. Okay, so that's how we use the integer or the immediate in branch. Okay, so to recap, if we want to use branch, this is how we're going to calculate. Okay? If we take the 2 register and compare, and the result is false, we are not going to take the branch. Then our new PC will be just PC plus 4, right? Because we are just going to the next line. And if we decide to take the branch, now the destination will be just your current PC plus 4 plus the immediate that is encoded in your instruction times 4. Again, why do we need to multiply the immediate by 4? Remember? How big is an instruction again? 1 word, 4 bytes, 32 bits, right? So, which means that the immediate only tells you how many words apart, but the address is in terms of bytes. So that's why you need to multiply the distance, the immediate, by 4, so that you know how many bytes are apart. And don't worry about the PC plus 4. So from now on, just remember that when we count the distance of the destination, we start counting from the PC plus 4. And when we talk about the hardware later, we will explain why we will add 4 to PC instead of just count from your current line. Okay? So remember, when we have branch, what we need to do is starting from the next line and then count how many lines is the destination from the next line. And that's your immediate. Okay? So let's use an example here. Okay. I have a branch here, BEQ, and the destination is AND. You can see that AND label is here, right? So this is an I format. And let's find out the opcode. If you look at the MIPS reference sheets from CAT courses, you can see that opcode is 4. Okay. And RS, which one is RS? 9 or 0? Okay, so the first one is RS. Okay, so RS is register 9, so the number 9. Okay, and RT will be the second operand, which is 0. Okay, so now what about the immediate? As you mentioned before, the immediate is the distance between the next line, which is here, and the target, which is here. So now let's count. The next line is here. You have 1, 2, 3. So in this case, the immediate for this branch statement is 3. Okay. And since the instruction or the address grows downward because your program grows line by line, right, from top to bottom. So the address is actually going down by increasing value. Okay, so in this case, your increment should be positive 3. Okay. So here is another recap. Okay, so again, you start counting from the next line, which is at you. Okay, and then you count 1, 2, 3. So your immediate is 3. Okay. So now once you have all these fields, all you need to do is just put them together. I have the opcode, RS, RT, and then the immediate, and convert each field into the respective binary. Make sure that you follow the number of bits for each field. Opcode 6 bits, RS, RT 5 bits each, and then the immediate is 16 bits. And if you want, you can group them in groups of 4 and then come up with the hexadecimal. So this is branch statement. Okay. So when we think about branch statement, we need to think about some questions here. So does the value in branch field change if we move the code? So think about it. I have a loop inside the program, okay? So now you finish one iteration, you go back, right? Or if you have an if-else statement, if this is true, you go to the destination. So now if you move this structure to different parts of your program, does it affect the instruction in terms of the machine code? What do you think? Okay, so let me rephrase the question. If I have an if-else statement, so let me show you an example here. Okay. All right. Let's say I have if A equals to B, okay, and then you do this, right? And then you have else, you do this. Okay, so now the question is, if I copy this group of program into another part of my program, okay? Now, these are the address, right? And definitely the location of this code will be different, right? Which means that the address will be different. But now what if I do B and E and then R1, R2, and then ELSE, right? So if it's not the same, I will go to else, right? So now this else, remember, is PC relative, which means that it's based on where it is. Okay, where the branch not equal is. So let's say, let me do this. And then I have ELSE here. Okay, we know that in this example, the immediate is what? You're starting from PC plus 4, and you count 1, 2, 3, 4, 5. So basically your BNE is what? Is BNE R1, R2, and then 5. So my question is, when I copy this code into different parts of my program, my address will be changing. Agree? But do I need to change this 5? What do you think? I can't see you, so you tell yourself, okay? So yes, the answer is no. You don't need to change, because as long as my program structure is the same, which means that I'm not adding anything inside the code, right? If this is the same, the distance between my BNE and else will remain the same. So that's why the number 5 here will remain the same. So no matter where I put this branch in my program, this 5 remains constant. Is that okay? Okay, so just think about this again, okay? So because when we use branch, we encode the difference between the destination and your current PC, okay, as immediate. So it's not an absolute address. That's why when we move this code to anywhere in our program, it doesn't affect the distance. Okay. All right, so let's go back to the lecture slides. Bear with me, because I'm still new to sharing screen, these kind of things. Okay. All right, so let's go back to our lecture slides. Okay, so now let's continue with the slides. So the next question is, what if our destination is further away, for some reason you write your if else statement or your loop having the body that contains more than 2 to the power of 15 lines of code. What can we do? Okay, so think about that. And why do we have that many ways to address the address or to describe the address? Okay, so why don't we have a consistent way to do it? Well, as we mentioned, right, because we have different formats of instruction, and different format of instruction requires us to use different bits to store information. So that's why it's difficult to have a unified way to store information. Okay, all right. So that's what for I format, and I'm gonna take a break and stop this video clip, and then I will have another video clip for J format instruction.